So accordingly, let us take a good hard look at the sum. It is clear that we're going to have to add terms of the kind k times b of k, and a little algebra ahead of time will smooth the pathway. So accordingly, let's identify a typical term in the sum, k times the binomial probability associated with k successes. Write down the binomial probability, and now we've got a simple algebraic equation to deal with. If we want to simplify it, we should begin by taking the binomial coefficient and writing it out in terms of a falling factorial and a factorial in the denominator. Now we're getting a messy-looking, more complex expression. We're trying to identify the row of k here. Remember, k is what I'm going to be adding over. K is going to range between 0 and n in the sum. I notice that the factor k multiplying the expression is in the numerator, and there's a k factorial in the denominator, which means I can cancel k in the numerator and denominator. Let us go ahead and directly do so. And now we've got a slightly, ever so slightly simpler expression with k minus 1 factorial in the denominator. This is an algebraic excursus, and it's not clear that anyone could really love that expression, perhaps not even its mother. But if we want to make progress in simplifying it, we should look for some themes here. And a clue is pointed to us by the appearance of k minus 1 factorial in the denominator that is beginning to be suggestive of another binomial coefficient, this time involving k minus 1. Let us see if we can massage the expression to make this dependence on k minus 1 evident. First, in the numerator of the fraction, we have k terms. Pick the first one, let's say n, and move it out of the fraction. That will leave us k minus 1 terms in the numerator. You have a product of k minus 1 terms, each one less than the preceding, starting at n minus 1 and ending at n minus 1 minus k minus 1 plus 1, or in other words, ending at n minus k plus 1. We make a little progress. Our next step is to observe that the power of p can be decomposed into a product of p with p to the power k minus 1. Again, a k minus 1 emerges. Take the extra factor p and move it out of the fraction to the left. Now what do we have? Well, let's simplify it. We pulled a term n and a term p out of the expression, keep it on the left and hold it, and then what remains is a fraction, a falling factorial in the numerator, starting at n minus 1 and proceeding for k minus 1 terms. Notice I've replaced the last term, n minus k plus 1, by simply subtracting 1 and adding 1 back into the term to make the dependence on n minus 1 and k minus 1 manifest. Then I've got p to the power k minus 1, and finally a power of q, which I can decompose by again subtracting 1 and adding 1 and writing it as q to the power n minus 1 minus k minus 1. That looks horribly complex, but you realize that the expression, the fraction, is just another binomial coefficient. It is just n minus 1 choose k minus 1. And immediately, the term multiplying n times p becomes identified with yet another binomial probability. And here is a key binomial identity. On the left, I have a generic integer k times the binomial probability b of k. Now let us identify the roles of the parameters n and p explicitly. So on the left, we have k times b sub n of k and p. Think of k as a free variable. N and p are your fixed parameters. On the right, I have n times p times the binomial probability corresponding to k minus 1 accumulated successes in n minus 1 tosses of your coin with success probability p. And now we've got a beautiful identity. On the left, we have a default experiment involving n tosses of a coin. On the right, we have connected it to an experiment involving n minus 1 tosses of a coin. It's not clear that these kinds of algebraic manipulations have taken us much further forward. But a little experience will tell us that we've done something very useful. We've taken a multiplying factor k on the left and replaced it effectively by something which doesn't depend upon a free variable, by a constant n times p on the right. This is going to pay us big dividends. But before we jump ahead of ourselves, this kind of general algebraic formula is valid for all choices of k and all choices of the parameters n and p. We can get a whole host of other formulae simply by replacing k and n by different values on both sides of the equation. So, for instance, if I replace n by n minus 1 and k by k minus 1, I get an equivalent formula. Just conduct the replacements on both sides, and now I've got an expression on the left involving a default experiment involving n minus 1 tosses of a coin, and on the right, a connection to an experiment involving n minus 2 tosses of that coin. We already have enough here to go ahead and compute the expectation, but this algebraic maneuvering is suggesting that there are other possibilities. So let's take a little detour with a view to later necessity and pick up one more identity.